Welcome. I'd like to thank everybody for coming to this evening's Department of Mechanical and Electrical Engineering Senior Design Project presentations. We have quite a lot of fascinating and exciting projects to have you view. This is Channel B, and for our first presentation of the evening, the ENSCO group will be presenting. Their advisor is Dr. John Dixon. Members of this team include Jared Gay, Isaac Groft, Josiah Isles, Paul Owens, Zach Peterman, Adam Sweet, David Vaccaro, and Zach Walter. The format of the evening will be that the team will present for 30 minutes and it will be followed by 10 minutes of questioning. At that point, we would ask you to open your mic and ask your questions freely. So let us begin with our first presenter for the ENSCO Rail team.
Wonderful, thank you, Dr. Klaus. My name is David Vaccaro, and this is the ENSCO Rail Senior Design Project for 2020-2021. This year we were working on ENSCO's TGMS, or Track Geometry Measurement System. It is an apparatus that is fixed to the front of a pickup truck, specifically modified to drive on the railroad tracks. Our goal is to modify a train axle in order for it to exert up to 2,000 pounds of lateral load as the truck moves down the tracks. This simulates the force generated by a fully loaded freight car. As the axle extends and applies the force, it also will take measurements on how much the track moves. The standard track gauge is 56.5 inches or 4 feet 8.5 inches. If the integrity of the track is diminished and this gauge is not uniform, catastrophic derailments could occur. Our measurement system allows for these sections of track to be pinpointed and replaced before these catastrophic failures could ever occur. One of the first steps we took at the onset of this project was to analyze the contact point between the wheel and the track. The wheel rests on the track at a very slight angle, so it was necessary to make sure that the weight of the truck would be enough to keep the wheels secure. Due to this angle, the force from the freight car is approximately 2,000 pounds, but when talking to ENSCO, they let us know that a typical lateral load that the track would see would be closer to around 1,000 pounds. So when taking over last year's project, we looked through to see what direction they were taking and if we wanted to continue in that way. We opted to redesign the spindle and add a hard stop to ensure a safer product in the end. We refined the construction, and the additional scope of creating a hydraulic system was added, which encompassed specifying pumps, motors, and related connections, as well as the directional and pressure control valves to allow for force regulation. And now Isaac will discuss the steps we took in the manufacturing.
So one of the first questions that needed to be answered was how we were going to approach it. So we took the design from the previous year's team. This was a second iteration of a project due to outstanding circumstances. And how do we turn the image you see on the left underneath the truck to what we have on the right? So the first component that plays a large role in the functioning is trying to keep the rotational motion of the wheel on the end of the axle from transmitting through all of your components. We have wires that are routed through the center of the axle, and if they rotate, you're going to tear them off. So we actually looked to the agricultural industry for this idea, and as simple as the one it is, the original concept was to use a set screw, and that concept didn't prove out well under stress analysis. So we decided to go with the non-circular cross section, which you'll see a picture of in the next slide. So on the left, you can see a hard stop and a sleeve. The sleeve is basically an adapter to go from the existing internal axle to that odd cross section that we desired. The hard stop, which was mentioned in an earlier slide, was integrated to the end of that through a weldment joint. That was intended to keep the axle from overextending itself. The components that we had from the axle from the manufacturer that we modified, the end of the spindle was only so long, which meant our hydraulic cylinder could actually push it out beyond the length of the spindle end. So to prevent that, we had had to add the hard stop in. And that's the inside of the axle. So you can see that was a press fit, but as an extra measure of security, we welded the sleeve into the axle. So internal to the axle, what transmits the power from the hydraulic cylinder to the wheel itself is what we have named the guide rod. So the original design for the guide rod from last year is on the left. On the right is the new design, and that was again modified to accommodate the hard stop. And here you can see, although we compromised a little bit of the integrity, we had to make the decision in order to prevent the axle from tearing itself apart. So we had to sacrifice a little bit in the strength category, although our factors of safety never dropped much below 5. So this is a breakout of the axle components. The red components on the left and right of the screen were leftovers of the original axle. So the general manufacturing concept behind this design was take a factory high rail axle and cut it in half, basically. And then the yellow pipe section that you see in the center with flanges on it is centered with the section you just took out. It is the same length as the hydraulic cylinder. The hydraulic cylinder will slide in it, as you can see in the bottom photo. And then the real challenge was, and we have to thank Jim Peich in the shop for this, maintaining the distance you're looking for over top of that distance and the diameter. You know, you're over 50 inches. The diameters are between 2 and 4 inches. Grove City shop is well equipped. This was a challenge. Jim promised me at the beginning of the manufacturing he would maintain plus or minus 1/32 of an inch across the entire length. Even though I may or may not have messed one of the parts up, he hit his 1/32. So very impressive coming out of Grove City College's shop. So another concern that we have is the application that all of these components are going into. It's a very unpredictable. The only thing we know is that it's going to be unpredictable. So in order to take extra precaution with the controller that we're using, it's a microcontroller that we borrowed from the Sparky department, we integrated some vibration dampening mounts into anything electronic that we want to protect and isolate. So Jared could not be with us this evening. He had other things going on that I guess he couldn't get out of. So he's going to discuss the loading situation and the analysis of the axle. I'll give you just a quick rundown. Basically, the 900 pounds is roughly what we could figure that the truck was going to apply to the axle, and I'll let him explain the rest.
Isaac, we can't hear Jared.
Okay, give me a second. Still can't hear him?
Not yet.
No, we still can't.
Nothing's coming through.
All right. Well, I will go over Jared's slides. We were prepared for this. It worked in our trial, but so on the left-hand side, you can see the spindle. We had to account for the axial load and also the radial load. So the axial load's coming from the hydraulic cylinder pushing out, and the radial load is coming from the truck pushing down. As you can see, we wound up with about 12.7 KSI as our maximum stress there, which we deemed to be plenty in the safe zone. Now that component was also of concern because it's a wear component. The sliding mechanism of the axle, oh boy, the sliding mechanism of the axle would tend to wear that component out. So we definitely wanted to make sure that we were well under its operating limits. And the same with the spindle, same loading conditions as the sleeve. We wound up with basically 3 KSI on that one. So the hard stop, the primary load on the hard stop, and the only one we chose to analyze was the axial load of 2,000 pounds. It's unlikely that will see that 2,000 pounds for a prolonged period of time. It is there to keep the hydraulic cylinder from overextending, and at the point of overextension, the controller will shut down the hydraulic cylinder. So that is, although it's around 33 KSI, the long-term function of that we deem to be still reasonable. Now, the guide rod, as you can see on the right-hand side here, was under a 2,000 pound axial load and a 900 pound radial load, which is the same as we tested everything else with. The big difference here was we wound up with 65 KSI, which was very concerning. And we milled this over for quite some time, and Jared and I finally had a conversation one evening, and we decided that we needed to run FEA on the entire axle to see how much load we were actually getting to this component, because we were basically loading this as if all of the weight was bearing down. So after we did FEA or ran FEA on the entire assembly, we wound up with about 3 KSI. So very minimal going through this to be concerned about.
So I'm going to be going over, my name's Adam Sweet, I'm going to be going over the hydraulic system that we integrated within this project. And this is really the guts of the operation, because that cylinder does not move at all without the hydraulic system doing exactly what it's supposed to. So we have a couple main components to the system, namely the reservoir, the pump and motor assembly, the hydraulic manifold, which includes the valves, as well as the axle itself, from which and to which the fluid goes to actuate linearly with a set force. So in order to achieve our goal here, we had to get some very specific valves, and included in those valves are the REO6 proportional pressure relief valve, which takes a command signal of 0 to 10 volts depending on how much pressure you wish to output to the cylinder, as well as a double solenoid directional control valve, which when you actuate those solenoids, when you send an electrical signal to them from our 12-volt battery, what happens is they divert flow to the cylinder, to the end of the cylinder that you want to actuate. So this is all done within the hydraulic manifold that these valves sit on top of. So this was a very complicated process, and one that was very difficult to find a solution for, because hydraulics is not covered in our curriculum here at Grove City. So this was an entirely new field. So it was one of our main design challenges, was figuring out exactly how we're going to do this and how we're going to get these valves to work as we want them to. In the end, they ended up working just fine. So that's a success. Now, there's also a control system that I designed for this project, which is really how we're going to get the force control that we're looking for. Remember, the whole goal here is to put 1,000 pounds of force laterally on the outside of the axle. So what we want to do is we want to set that force at the very beginning. We take that and send that signal to the controller, so this controller knows what it wants to be setting the valve conditions at. Now, when the valve conditions are set, ideally, then we'll output 1,000 pounds of force on the axle. However, we also want to run this signal back to the controller so that it gets a readout of the actual force that's being applied. From there, it can output it can reset the valve conditions to what we want, and then it can continue to match that force continuously. So the whole idea here is to take the force readout and use it as a control loop to get that force readout constantly hovering around 1,000 pounds. Now, in order to do this and to verify it, we also have a distance measurement tool, which Zach Walter will go over later, which allows us to confirm that the axle has extended, and in general, it just assures us that the axle is working as it should. All of this is controlled through LabVIEW, which is a graphical programming language. So what I did was I wrote code in LabVIEW to take our inputs from the load cell and the distance readout to get an idea for what the force will be that the axle is outputting currently. So once we have that, then we can send control signals to the REO6 valve, which, remember, takes a 0 to 10 voltage, as well as the directional control valve, which is just a single binary on-off to either end of that valve, which can divert flow to either end of the cylinder. And all of this works together in order to output that constant 1,000 pounds on the force, or by the axle on whatever it's pushing against.
Hello, everybody. My name is Zach Peterman, and I'll be talking about the pump and motor assembly here. This pump motor assembly, it powers the hydraulic system, and it is composed of a 12-volt motor, a Lovejoy coupling, a motor mounting adapter, and a hydraulic pump. So in order to find the best pump for our situation, we need a pump that created a flow rate capable of powering the hydraulic cylinder to adjust at an appropriate rate, while also minimizing the temperature increase of the fluid running through the system. Picking the right motor involved a motor that could run for 30-minute to 1-hour duty cycles without overheating, along with having the right RPM and horsepower for the pump. And the horsepower equation is shown on the slide. Here we have an internal view of how the pump and the motor are connected. As you can see, the shaft coupling, it connects the different shaft diameters between the motor and the hydraulic pump. And not only does it connect them, but it adjusts for certain vibrations or also axial misalignments between them while it's running. So it has a secondary benefit to that as well. So this is the reservoir that we chose. It's a 5-gallon reservoir, and you choose the volume of the reservoir based on, rule of thumb is you take 3 to 5 times the flow rate, and that would be the reservoir's volume in gallons. It has features such as a breather cap, fluid level gauge, and also a thermometer. So due to the hydraulic cylinder having metric ports and the reservoir and pump having English ports, it did create a bit of a challenge connecting all the components. Luckily for us, though, we chose a manifold assembly that has metric ports, which allowed easy connection to the hydraulic cylinder. The reservoir and the pump, on the other hand, were English, so they did need multiple adapters to convert to the correct size for the hoses. And for the hoses, we chose a small diameter hose, which was just a 3/8 inch inner diameter. So this is the frame for the skid unit, and it is composed of a 1-inch steel square tubing, which is welded to the top sheet, as you can see in the image. And the function of this is that it provides support for all the weight that's going to be on it, and it also allows a gap between the bolts connecting everything and the bottom surface that it will be sitting on. And so this is the skid unit. You can see all the components listed on the left matched with the numbers on the image on the right. And you can also see how the hydraulic skid unit connects to the hydraulic cylinder and the axle. The biggest part and challenge to designing the skid unit was making it big enough to fit all the components and having it all fit, but also making it so that the hoses had proper bending radii and you kept the profile small and lightweight. All of the components are bolted to the top sheet, and it utilizes an overhead crane hoist rings connected. There's 4 of them, and those will allow for easy movement while all the components are attached to it because of the additional weight with all the components on. The system draws electricity from a 12-volt deep cycle battery, which will then power the motor to drive the pump, running fluid through the system. And with that, I'll hand it over to Paul Owens.
Hi, everyone. I'm Paul Owens. And as Adam said before in his talk about the feedback loop, the load cell is very important to that feedback loop in getting a load reading out to our control system. So we tried to find a load cell that would best serve our purposes. And one of the options that we took a look at was the pancake load cell, as you see on the right. Where we would place that would be between the hydraulic cylinder, which is in the center of the picture there, and between that and the axle on the right. Now we decided against this option because if you look at the picture of the pancake load cell on the right, the small hole in the center is the only connection that the load cell would have to the rest of the axle, and thus our axle will be riding on that very small diameter point of connection. So we instead decided to go with an inline load cell, as you see on the left, which goes between the left side of the axle and the hydraulic cylinder. Now, some challenges we had with selecting this load cell was it's very customized, and we had some requirements, as you see here, that made it difficult to find a vendor who would provide a load cell that would meet our needs. So we needed it to withstand 2,000 pounds and be able to give us a load readout at that poundage. And then we also needed to be calibrated in compression, sealed to IP65, which means that it is water resistant but not completely waterproof. We also need it to fit within the 2.25-inch axle, and this was the most difficult thing that we had in selecting this load cell, because that's a rather small area for both the wire and the body of the load cell to fit within. And due to our hydraulic cylinder being metric, we were forced to use M27x2 metric threads, and we had a female and a male end. So the picture on the right, as you see there, has 2 male ends, but our model had just 1. You can see it here threaded onto the hydraulic cylinder. As you see, the wire routing there comes out of the side, or I guess the end of the load cell instead of the side of the casing. If you go to the next slide, we'll talk about that a little bit more. So here's the placement of the load cell between the hydraulic cylinder and the guide rod. And here you can see a cross section of our load cell in blue there, and then you can see the blue wire coming out of our axles there. So if you see the red and the yellow are 2 diameter axles that we had to route the wire through, and the brown is our hydraulic cylinder that threads into our load cell. And one of the issues that we had with the threading for our load cell is that the hydraulic casing actually rotates as well. So if that were to occur, while the truck is in motion on the rails, then the wire could potentially get wrapped around the rod of the hydraulic cylinder. So going forward, there would be maybe some better considerations to be made for that wire routing to make it a little bit easier to assemble. So the load cell outputs a signal, but only at 2 millivolts, which isn't enough for a typical data acquisition unit to receive. So we required an amplifier to bump up that voltage from that 2 millivolts to 5 volts. So we selected this amplifier, as you see on the bottom left. It's very small, and it fits inside of this inline housing that was provided with it. So we soldered those up, and we actually attached that to the axle. And next, Zach Walter will speak about the measuring system.
Hi, as Paul said, my name is Zach Walter, and I'm going to be talking about the measuring system for sensing deflection in the rails when a force is applied. We looked into some various sensors, including the ultrasonic, laser, and light sensor. And after some research, we narrowed our options to the ultrasonic and light sensor. The laser sensor was too expensive and too fragile to be mounted externally onto the axle. And the ultrasonic sensor turned out to not be compatible with the MyRio control system. So our final selection was a light sensor, as you can see in the picture. The sensor cover mount seen on the left side of the picture, it's the box there made out of 1/8" plate. We designed that to protect the externally mounted light sensor from elements such as rain, dust, or debris. The sensor reflector plate seen on the right side of the picture was designed to provide a consistent measuring surface for the sensor to view. The plate mounts to the spindle hub on the dynamic side of the axle, and it maintains clearance from the wheel. And next, Josiah will be talking about our budget and some of the testing that we performed. Thank you.
My name is Josiah Ilias. I'm going to briefly review our budget before I get into some of the information on testing. So for the semester, we were offered by ENSCO $5,000 for our budget. ENSCO really gave us a challenge with working on the hydraulic system and lots of electronics for us to work on. So we ended up spending a little bit more, nearing $7,700, but we had some very expensive valves and other sensors, and obviously a large amount of parts that we had to order. I also want to quickly thank our ENSCO representative, Ron Lang, for dealing with all of the orders and all of the emails that I sent to him asking about lead times and other orders. So I just want to review some of the troubleshooting of the pump and hydraulic system that we took on the first 2 days of testing. So when we first went to run the hydraulic system, we turned on the motor and we went to actuate the D1VW, and nothing was reaching our actual cylinder, and we couldn't get any extension on the axle. So to troubleshoot it, we first, since we did not feel any flow in the hosing that comes from the manifold to the actual axle and cylinder, we removed those hoses and then ran the pump again. We realized that we're actually drawing a vacuum on those hoses instead of pushing fluid through it and getting pressure to the cylinder. So we had to really troubleshoot here. We kind of figured that maybe possibly the hydraulic fluid is taking a wrong path through the manifold. It could be skipping the D1VW completely and having zero extension. So we actually removed the RE06, blocked off those ports with a steel plate, and tried to force fluid into the D1VW. And after that, we still were getting nothing. We even ran it without the steel plate and with open holes in the system that were directly connected to the pump. Not even fluid was coming out of those holes. So big learning moment came here in our process. We looked at our motor and decided to switch the polarity on the motor and realized that we were actually running our pump completely backwards. And after we turned it on, we hit the on switch and fluid shot out of our manifold and fried our breadboard. But then we realized what we were doing wrong, and a big learning moment for us. And I'm going to have Mr. Sweet continue on and talk about some of the troubleshooting with the RE06.
Yeah, so when it came down to it, there's a few key design challenges that we had here. And really the most expensive component of our system was that REO6 valve that I mentioned before, the proportional pressure valve. And we were having some trouble getting it to work exactly as we wanted to. So what we did was we broke it down into a series of steps and traced the fluid flow from one component to the other to make sure that everything was operating the way it should. Now this is interesting because all of these devices that we're talking about are all electromechanical. So they are powered through electrical connections and things like that. So not only do those connections have to be right, but also then you have to care about the mechanical actuation that they're going through. So it really complicated the process because not only you're concerned with multiple aspects of their operation. So not to mention the fact that we cannot run these devices right off of our controller. It would be great if we could send a 10-volt signal right from our controller to power up each and every valve, and that was it. But the solenoids, especially on the directional control valve, which directs flow to either end of the cylinder, the solenoids on that valve are 10-watt, 30-amp solenoids. So our MyRio, the controller that we were using, is not nearly powerful enough to do that. So what we ended up doing was using a relay and using a trigger system. It's just a standard automotive relay, and that worked really well to get our valves to actuate. And also it just ended up allowing us to have force control, which is exactly what we were looking for. So I'm going to play a video here on the next slide that demonstrates the fact that we did achieve force control. If you can see, the cylinder will extend a small portion, and then it stops because the ratchet trap there provides enough resistance to stop it. Then what I do is I increase the voltage to the REO6 valve, and the cylinder extends more, showing that the pressure has been boosted, and that's a directly correlated factor there. If the cylinder is extending more, then the pressure has certainly been boosted. And so at that point, it's just a matter of calibration, and ENSCO will be able to take this and run with it because it is a working prototype. So we're very happy with the result. So anyone have any questions or anything else, feel free to offer that.
So this is the time that if you do have some questions, please open your mics and ask them.
I have a question. Did you guys do any hand calculations to verify your FEA?
I don't believe there was too many hand calculations done. I would have to, unfortunately, Jared, the one that's not here, would be the one to answer that because he was the one that did all the FEA, and that was done last semester. There may have been a little bit, but it was almost exclusively done in Creo.
Did you test the system on a rail?
The system has not made it to the tracks yet for several reasons. We don't have the truck to mount it to, and it relies solely on the weight of the truck. So we would need many components we don't have. I guess something else that adds to that, the testing photos and videos that you've seen have been over about the last week. Lead times on hydraulic material right now are very, very long. I believe the 2 valves we waited between 12 and 16 weeks to receive, which when you have to wait, when you have to know what you want first, that really throws some difficulty into the equation working within a 2-semester window. So the answer to your question is no, they have not made it to the rails yet, but we have the ability to prove out the software to the best extent we can on the lab bench.
I have a question. Did you consider the possibility of putting pressure sensors in your system as kind of either a second way of checking on the load that's actually being exerted, or possibly even using that?
Yeah, I can speak to that, Dr. Fair. We did briefly consider the idea of putting something like a pressure transducer somewhere on there to verify. We also kicked around the idea of putting a pressure relief valve that was not adjustable. That was kind of one of our initial designs. So that would have been another step that we could have used to verify the pressure, because a valve like that would just blow off anything beyond the pressure setting that you have for it. Now, we ultimately went with a pressure regulating valve that will set the pressure exactly as we want to. So yes, to answer your question, we are confident in the REO6 valve setting the pressure that we would like, because that's exactly what it's designed to do. But I do understand that, and a pressure transducer would also be a good approach for verification. But we did not implement that, but that would certainly be a valid way, and I don't see why you couldn't do that.
I can speak to, I believe that was Mrs. Henley asked about the hand calculation. The previous group had done, in the previous year, had done, beam analysis type hand calculations looking at the loads, but that was about the extent. So they were fairly rigorous, but they were largely completed in the year prior to this group taking over. John Dixon speaking.
Ron Lang here from ENSCO. Want to check, make sure audio is working. Can you hear me okay?
Yes.
Yes, we can, Ron.
Hi, I just want to say we at ENSCO are very excited, very pleased with the progress and the results of this year's team. We threw a lot at them, and a project really doesn't get any more real world than this. The team was able to take an existing design that was started last year and taken through a concept. This year, the team took that concept clear through to a mature design mechanically, and then on top of that, we threw the hydraulic control system at them, and the team took that challenge to heart and split up the team into functional groups and really took an initial design clear through what we see as a usable prototype. So we are very proud of the team and excited in our sponsorship of the program and of specifically this project. And an answer to the question of has the system been on rail yet? No, we heard that, but we at ENSCO are excited to take that next step. So that's next. We have the high rail vehicle available, and we're ready to put this on and put it to the test in the real world. So bravo to the team, congratulations, and job well done.
Thank you, Ron, and thank you, team. Congratulations. And so as you can see, someone's applauding you. We all do. Good work.
One last thanks from the team, Ron. We appreciate your sponsorship and working with us through this project.
You bet. It was fun. Even all the parts ordering, all very fun. So yeah, and again, it doesn't get more real world than this. We had some parts we were trying to order. Lead time was 10, 12, 16 weeks. Some of that stuff we were able to get on order in time to have it in hand. Other cases, we were looking for a hydraulic hose, which should be a lead time of 1 or 2 days, and we got lead times of 4 and 5 weeks. So we had to find alternative vendors. So it was all real world engineering, not only the design questions, the you know where the high railer hits the track, as you will, and actually getting a hold of the components in time to put it together and make it all work. So it was very real world this year, and really a very fun project for us to sponsor. So.
Yeah, and I'll echo some of Ron's comments there. I mean, the team just did a fantastic job. They really stepped up to what ended up being quite an immense technical challenge implementing this hydraulic system. So again, just really proud of you guys. Fantastic job.